I'd like to make a set of 3 videos that kind of touch on how to build and shape Lewis structures, and then how to relate that to phases and intermolecular forces, because they're kind of related. How, I guess, a molecule looks relates to the forces between them. So the first thing this video is going to touch on is building Lewis structures. So also after this video we'll have one on shaping them according to Vesper theory, valence shell electron pair repulsion. We're going to use 3 rules for building. They're going to kind of be finding the number of valence electrons, and then we're going to have to second find the middle and frame. So find middle and frame around it is part of, and then add all the other electrons in. So there's 3 really, I guess, parts to this building. It's finding the number of valence electrons you can use to build with, to pull things together, atoms. And then second step is to find out which atom goes in the middle and put all the others around it. That's kind of the framing. And then last will be adding the other electrons in, and we'll have I guess one more step on that. But also just wanted, again, just tie together in the second and third video. Maybe the third video will be about phases and intermolecular forces. So just to kind of give you an example of this, you can build water, a Lewis structure, and this would be a valid Lewis structure. It has the atoms, the oxygens of greatest need. He's in the middle. He needs 2 bonds. H's only need 1. And so we can build it, but we also need to shape it. We know water is not linear. It's bent. So we need some rules for that, to know how to shape it, not just build it. So it has an angle here of about 105 degrees. But we also need to know something about bond polarity. We need to know that oxygen has a greater desire for electrons. It pulls electrons towards itself through these bonds, and it makes this part of the molecule of water partially negative. It makes these H's partially positive. It has overall polarity. Well, this plays into then its phase behavior and the forces between water. And I'll close with this. If that's true, then we can understand why, I guess in pictures you'll see an oxygen of one water molecule close to a hydrogen of another water molecule. These little dotted lines often mean you have some weak intermolecular forces. Intermolecular forces aren't covalent forces. They're more just weak associations due to electrostatics. You have a partially negative oxygen here next to a partially positive hydrogen. So it's favored to have that orientation, whether it be in the solid phase or the liquid phase. And of course everything that's in a gas is very far apart, so this sort of doesn't become a part of that story. So let me go ahead and keep on going and say a little bit then just about the first part of building Lewis structures. Lewis structures reveal the connectivity of atoms. We need to first, of course, determine the number of valence electrons, always. So just going to amend some of these steps here. Always determine the number of valence electrons. And so then we have to, second is determine determine an atom of greatest need. So I put that back in here, determine number of valence electrons. And this step will be, I guess, will not be referred to after this slide, but we'll always need to determine, before we start anything, the number of valence electrons for a Lewis structure. And I'll show you how we do that. Again, the second step is determine the atom of greatest need. The third step is to draw the frame and fill in with electrons from the outside to the inside of the structure. And we'll consider resonance forms and formal charge after we do these steps. I'm going to stop there, and we'll come back and fill in on our next video understanding the shaping of the Lewis structure and the charge. Well, just to kind of review before we start making molecules, let's just talk about atoms and how to determine the number of valence electrons for each atom. So we can do this work of finding valence electrons by doing the following. Count the steps to the atom in the periodic table. So for example, we were to look at boron. Boron is 1, 2, 3 steps from left to right in. So we'd write our B and we'd say we have 1, 2, 3 electrons. You kind of go around to each side and make sure each side has 1 before you come back around. The next one we could say is carbon has 4. So we could put 1, 2, 3, 4. But nitrogen, being that it's 5 valence electrons, or 1, 2, 3, 4, 5 steps over, we can say 1, 2, 3, 4, and then we come back around and we put a pair together. So this kind of is noted here. To start drawing the dots, make sure to work around the atom, or the case chlorine, to putting a dot on each side, and then pair them up as you go back around. So with nitrogen, we just went to one, what we call pair. Now it doesn't matter where that shows up. So for example, here we have the 3 pairs on the left and 1 unpaired on the right. We just need to make sure we go around starting at any point and walk to each side first. So you can go to a video if it's available that'll help you with that. Let's go ahead and build from there. How do we deal now with building structures from atoms? Well, we can take again, determine the number of electrons for each atom. Hydrogen would have 1 and bromine would have 7 valence electrons. And we need to know when to stop bonding. How do we know how many H's go around this bromine? Well, the key is to remember the octet rule. That for most elements other than hydrogen, they want to receive or achieve the octet state, meaning they want to make number of bonds necessary to have 8 electrons around them. So he only has 7. He needs 1 more electron, and he's going to do that through bonding. Remember, these are all nonmetals. Nonmetals gain their octet state not by stealing, but by sharing electrons to achieve that state. So he needs to share his 1 unpaired with another unpaired to make a bond between H and Br. We now have a pair between them because they both shared, and that gives the bromine 8 electrons, and it gives the hydrogen just 2. Hydrogen is only needing 2 to fill up its valence shell to be like helium. So we can do this game. We can play it for sulfur and hydrogen. Sulfur needs 2 more. If we can just maybe fill in circles to say he's missing 2 spots, or he's only got 6 electrons, he needs 2 bonds to receive, I guess, 8 electrons around him. He needs to have 2 of these. And then of course you can play the game. Nitrogen has only 5 around it, so he needs 3 more electrons to achieve octet state, and therefore he has 3 bonds. So well, there's not 3 bonds here. Yeah, there are. It's called a triple bond because it's between the same 2 atoms, 1 bond, a 2nd bond, and a 3rd bond between 2 nitrogens, and each nitrogen, if you count that up, has 8 around it. It might be sharing or unshared, but whether it be sharing or unshared, there's 8 around each. So look at this lone pair, not shared, but it's still counted for this nitrogen. So 2, 4, 6, 8. And then this nitrogen has his unshared, but he also has 2, 4, 6, 8 electrons. So each of them has 8. So I hope you've kind of been convinced that we can bond using nonmetals to achieve octet state, and that's when we stop. Now there's different ways we can draw Lewis structures. I'm going to, from this point on, go with just lines. So instead of drawing just all the dots, we can kind of designate these lines as sort of the bonding electrons. They're the electrons that were shared between 2 atoms. And these will be the non-bonding electrons. They're also called lone pairs, non-bonding electrons. And the number of bonds off of the oxygen is 2 because it needed to have 2 bonds to reach an octet state. The number of bonds off of nitrogen, 3. And then the number of bonds off of carbon will be 4. Remember, each line in a Lewis structure is 2 shared electrons, and the remaining dots are unshared electrons, which are owned by the atom they sit on. So these 2 right here are owned by the nitrogen. All right, moving right along, we're just about 3 more slides away from finishing with an example problem. Thank you for hanging in there. Excuse me. So let's try an example problem, CH4. What is the number of steps for carbon to neon? So if you look at a periodic table, I hope you're noticing that carbon needs 4 more electrons because it's 4 steps to neon. And in the number of steps from hydrogen to helium, we know it's just 1. So we know kind of how many bonds we're going to make. Carbon's going to have 4, and each of the hydrogens is going to have 1. So 4 bonds for carbon because it needs to get to that number of electrons through bonding. And hydrogen just needs 1 more electron. It does that through this 1 bond. So we take these and put them together. Just have kind of orbitals representing where the electron is. We pull all that together. We have 2, 4, 6, 8 electrons around carbon. He's happy. The hydrogens have each of them just 1, 2 around them. They're happy. And we have, if we just draw the lines, we have methane. Methane, this is the Lewis structure for methane. I just want to also touch on a simple rule. It kind of came from a fella, Daniel Gonzalez at Baylor, just kind of call it NO rule for formal charge. Now there's some formal rules for formal charges, and you can find that on a video I have available. This is just a real quick way to determine the charge for nitrogens and oxygens, just those 2. They're committed to always having 8 electrons around them. They're just more electronegative than other elements because they're on the right side. So this generally works. It's not perfect. It doesn't always work, but it generally works. If you have 1 less bond than what they typically want, they're negative charged. So N likes to have 3 bonds. So if it only has 2 off of it, let's say these are to hydrogens or something, then it has a negative charge. An oxygen, if it only has 1 bond off of it, let's say a carbon was sitting right there, then it would have a negative charge. So 1 less, it's negative. Of course, if it has the 3 bonds it wants, it's neutral. 2 bonds, it's neutral. If it has 1 more, let's say this is an ammonium ion, it has hydrogen sitting here, it doesn't really matter, it's just 4 bonds off of nitrogen, then it's going to be a positive charge. And again, oxygen, if it has 1, 2, 3 bonds off of it, it'll be positive charge. So kind of in summary again, just remember the NO rule. If N or O has 1 less bond than what they typically want, they're negative. If they have 1 more bond than what they typically want, it's 3 and 2, then it'll be positive. This one has 4 bonds, this one has 3. That's just kind of a simple, quick, real discussion of the NO rule when it comes to formal charges. And in general, most compounds want to achieve a neutral state, but that can be dependent upon the context or environment that the molecule sits in. All right, let's do 2 slides, and I'm going to kind of review the rules for drawing structures, and then we're going to apply that and we'll be done. So let's review. To find or develop or draw a Lewis structure, you have to determine the number of valence electrons. This is not, again, in the summary here, but you need to remember, always determine the number of valence electrons, for the formula they give you. Find the middle, the non-metal that's farthest to the left in the periodic table, or has the greatest need. You're saying the same thing. Build and frame around that the other atoms, add in the lone pairs, and then drop them down as needed to satisfy the octet rule. Now this part we haven't really developed, so we're going to kind of review that. And I'll be able to talk about all 4 of these real quickly with CO2. Now CO2, you are given the number of carbons and the number of oxygens, so you can kind of say, well, there's 4 valence electrons for carbon, plus there's 2 oxygens, so we're going to say 2 times the 6 for oxygen. So that's going to be, what, 16 electrons that we have to get into the story that we build, called the Lewis structure for CO2. Well, the middle is certainly carbon. Would you not agree it needs 4 bonds? So he gets to sit in the middle of whatever structure we propose. And if I'm going to propose a structure, I've got to have at least 1 bond on each side going out to oxygens. So we know that's kind of our frame we're going to build around. Well, we have to add in electrons. We have more of them because if I just have that frame, I only have 2 electrons here, 2 there in the gaps, and that would be just 4 electrons. I need to add in 12 more. So 2, 4, 6, 8, 10, 12 from the outside in. I'm adding those electrons. I added them on the oxygens on the outside. But you notice carbon's not happy here. So this fourth rule is going to kind of come in because I need to drop down these lone pair electrons. Remember, lone pairs were just non-bonding electrons. I'm going to make them bonding by just dropping them down to the gap. And that's not going to be enough because carbon likes to have 4 bonds. We know carbon likes to have 4, so I'm going to drop down another pair. And if I do that, I only have now 2 pairs on each oxygen. 1, 2. And then, of course, on the other side, just 1, 2. So this would be a final structure for CO2, the final Lewis structure, using lines in place of dots when it comes to bonding electrons. Now, I think I need to stop here just for sake of time. We'll apply this in the start of the next video to building a valid Lewis structure. Remember, the lone pairs and bonding electrons are different. Lone pairs are non-bonding electrons. They're equal to the number of valence electrons for all elements is, so the number of lone pairs equals valence electrons for all elements minus 2 for the number of bonds. So I guess we didn't really use this rule. We kind of just said, hey, we know the number of valence electrons to begin with. If you count up those for C and the 2 oxygens, it was 16. We know what the middle was. Carbon was the atom of greatest need. We built a frame around it. The oxygens have to be connected at least by a single bond each. So 1 bond here, 1 bond there. That was 4 electrons. We needed to add in 12 more. And 12 electrons. So we did that. We added in 12 electrons from the outside. These are the dots we added in. And then we had to drop down 2 dots, 1 from each oxygen, to give us a final happy Lewis structure. Carbon needed to have 4 bonds. The oxygens need to have 2 bonds each. As we know by just knowing about their nature. Oxygen likes to have 2 bonds. If it goes 2 steps over, it needs to have 2 bonds, and it does here. Carbon needs to have 4 bonds. It does. There's 1, 2. That's a double bond. 3, 4 lines off of carbon. Well, thanks. That's a little bit longer than what I wanted, but I hope that worked for you to help you understand how to build Lewis structures and some rules for that.